In this video, I'll introduce derivatives. A derivative is just the rate at which some parameter is changing, so it corresponds to the slopes I talked about in the previous video. One important aspect of derivatives is that they describe the rate at which energy in a system can change. The slope of a line is also called the derivative of the function describing the line. It's typically a function of the independent variable and is tangent to the function at the point where it's evaluated. The slope of a curve is the rate at which the function is changing with respect to some independent variable x. However, this rate changes depending on where on the curve you measure it. The rate of change is always tangent to the curve. So if I pick a point x1 here, the rate of change looks like this. If I change that and look at the rate of change at a different point x2, it looks like this. But no matter where on the curve I check the slope, it's always tangent to the curve at that point. Now let's talk about how to actually calculate the slope or derivative of a function. The function we're using is graphically represented by this line. We want to find the slope of this curve at some arbitrary point x on the horizontal axis. I'm going to pick another point a distance delta x away from that point and connect the 2 points with a straight line. The slope of this line is obviously a bad approximation to the tangent of the curve. So let's pick a smaller value for delta x. This is better, but let's reduce delta x again. Now, to get the actual slope, we need to keep making delta x smaller and smaller until it's almost 0. When delta x is 0, we get the actual slope or tangent to the curve at x. So we need to pick 2 points on the curve that are infinitesimally close together, connect those with a straight line, and that'll give us the slope of the curve at this value of x. Mathematically, derivatives are defined by letting delta x become 0. In numerical analysis, we can't do this step, since we'd be dividing by 0, which isn't an allowable process. The symbolic math in this case works out, since the numerator also goes to 0, and there are ways to deal with that result. The proper notation for a derivative is small d by dx of the function. The notation of using lowercase d's here rather than deltas implies that the limiting process of letting delta x go to 0 has been done. So far, we've seen why the slope or derivative of a function is important and how a derivative is defined. Our remaining problem is to calculate a derivative numerically. Our definition of a derivative requires us to divide by 0, or to calculate 0 divided by 0, which we can't do numerically. The next video will present ways to numerically estimate the derivative of a function or a set of data.